Hello, welcome to Olympiad geometry. Let's continue our study of the Menelaus theorem in the Olympiad math computation. So this problem is saying in quadrilateral ABCD, diagonal AC is angle bisector of angle BAD. E is a point on segment CD. BE intersects AC on point F. BC intersects DF extension on point G. Proof: angle GAC equals to angle EAC. So we want to prove angle GAC equals to angle EAC. We can see that we have a triangle BCE and we have a line GFD intersects on the triangle. And we want to prove that this angle equals to this angle. This problem is a very classic problem, and it has a lot of variants. We will prove those variants in following videos, but for here, we can simply use Menelaus theorem. Let's do that on the triangle BCE, and we can use Menelaus theorem on triangle BCE and the line GFD. So we have BG divided by GC times CD divided by ED times EF divided by FB equals to 1. If we look at one term of the BG divided by GC, this ratio can be related to the area of triangle ABG and the triangle AGC. So we can transfer, we have this one, right? But we can transfer each term, the BG divided by GC, to be the area ratio, that is area ABG to area AGC, and for CD to ED, it can be transferred to area ACD to the area AED. Similarly, EF to FB can be transferred to area AEF to the area AFB. We know this one equals to 1. Now we can let angle GAC equals to angle EAC equals to theta. It's easier for us to do the derivation of the following proof. So this is theta. We write it here, and we can let angle GAC equals to alpha, angle EAC equals to beta. Right, so we want to prove alpha equals to beta. We can extend the area of ABG to be half times AB times AG, right? ABG, that's AB times AG times sine theta minus alpha. And for AGC, that's AG times AC sine alpha. And for here, ACD, the area of ACD can be written as half times AC times AD times sine theta. And AED can be written as half AD times AE times sine theta minus beta. AEF, that's half AE times AF times sine beta. And AFB, that is half AF times AB times sine theta. This production equals to 1, right? And if we look at all the terms, we can cancel the AB, we can cancel AF, we can cancel AE, we can cancel AD, cancel AC and AG. All the 0.5 terms are cancel each other. So we have this equation. Let me write it here. So that's sine theta minus alpha divided by sine alpha. Notice that sine theta can be cancelled by sine theta times sine beta divided by sine theta minus beta equals to 1. That means sine beta sine theta minus alpha equals to sine alpha sine theta minus beta. We can extend this term, right? So sine beta times sine theta cosine alpha minus cosine theta sine alpha equals to sine alpha times sine theta cosine beta minus sine beta cosine theta, right? So the first term would be sine beta, okay, cosine alpha sine beta sine theta minus cosine theta sine, let me write it in order. So sine alpha sine beta cosine theta equals to sine alpha cosine beta sine theta minus sine alpha sine beta cosine theta, right? So the minus term are the same, the minus sine alpha sine beta cosine theta. So these two terms cancel each other. That means cosine, and we can have this this term, we move it to the left side of the equation. That becomes sine theta cosine alpha sine beta minus sine alpha cosine beta equals to 0, which means sine theta cosine, sine beta minus alpha equals to 0, which means beta minus alpha equals to k pi. So here we have to let k equals to 0, which means beta equals to alpha. And we prove that angle GAC equals to angle EAC. This is a very classical problem, and actually we later on we would see that we can change the position of this point C. We can push it on the point on a point that BCD are collinear, and we can keep pushing it inside of the triangle ABD. we have variants for this problem, and we will prove that in Seva series, not in Menelaus series. And this is a problem for today. So thank you for watching the video. See you in next video. Bye.